I want to turn now to look at the non-symbolic approaches. One of the earliest successes in this other wing of the development of artificial intelligence had to do with pattern recognition. And one of the earliest gains here was the use of pixelation of a, say, scanned image or a photographic image, and matching of the sequence of those pixels to a template to determine automatically whether a given letter was printed in the photographic field that had been scanned. And so if you think about this, again, based on what we know about computers so far from Turing and this early history of computation, it's not hard to see how this would be possible. If we have a 1/4 inch of paper on which a letter will be printed, and we imagine that there's a scanner that can kind of go from 1/4 inch to 1/4 inch across the paper. But we have a printed letter there in this square, in this 1/4 inch square. Then it should be possible to scan that, break the scanned photo up into, say, a 32 by 32 array, so that you've basically imposed a grid onto that square 1/4 inch of photographed paper. And then translate each of those pixels, code each of those pixels as a 0 or a 1, basically white or black, okay, empty space or marked space, 0 and 1, so that you have now a 32 by 32 array of zeros and ones. And then check whether that array of zeros and ones closely matches a template. That is, the template for the letter L, right, will have zeros through most of that 1/4 inch square of space through those 32 by 32 pixels, but will have ones, marked space, for a shape that looks like an L. And so, of course, what you scan with your scanner won't be a perfect match for that template, but you can, say, go for good enough. An 80 or 90% match will get coded as an L, and so on for other letters. And this worked very, very well for printed letters, in particular letters that were printed with the same font as was used in the template. And it became used for automating the reading of bank statements very early on. When it comes to handwritten letters, however, it's much harder, or designing a program that can code letters regardless of the font. Okay, so if the font isn't standardized, then it's, I will say, much harder is an understatement, almost impossible to just use a pixelate and match to template method to accurately code a text. So you need some other system for being able to recognize letters in handwritten or in multiple and varied and unfamiliar fonts. And one of the earliest proposed systems that turned out to be pretty good at that, at basically being able to be programmed, or as we would now say, trained, to accurately identify handwritten numbers and letters, symbols, and numbers and letters written in different fonts. One of the earliest systems to do that was Oliver Selfridge's Pandaemonium. This name means the place of all the demons. For some reason, theoretical posits in scientific fields sometimes get called demons because they're kind of imaginary creatures, so to speak. This architecture was described in this 1958 paper, and it was used for a variety of pattern recognition tasks. It's a hierarchy of demons, okay, almost like a employment hierarchy where the boss is at the top and there are middle managers there in the middle, and then there are entry-level workers there at the bottom. And the entry-level workers, so-called data demons, send information up to the cognitive demons. They send reports, so to speak, up to the cognitive demons. And the cognitive demons send their reports up to the decision demon. And so, you will give the data demons one of these 32 by 32 arrays. You give the data demons a scanned image. So the data demons are looking for a particular thing. The green demon may be looking for a circle, and the blue demon is looking for a vertical line. And they send messages up. They sort of call out and say, hey, we got one here, to particular middle-level managers, particular cognitive demons, okay, when they are noticing that feature. And then the mid-level managers send their signals up to the decision demon, and then the decision demon is charged with somehow negotiating between these or somehow weighting the different responses that have been given, the different information that is coming in to him or her. The decision demon then calls out which letter he or she thinks that is being presented in the input data. And Selfridge also proposes two possible mechanisms for improving a model like this once you have one. So in today's terminology, we would call these learning procedures. One is that we could have the volume of basically the arrows here be adjustable. And so it could be that when the blue demon calls out to R, that calling is weighted less heavily than the calling to R from the red demon. Likewise, it could be that the calling to the decision demon from the R demon is somehow, at a lower volume or a higher volume than the calling to the decision demon by the Q cognitive demon. And so this idea of adjustable volumes, Selfridge described as megaphones. So, I don't know if you've ever seen a megaphone, but they are, this little technology often used by police if they need to call out to a crowd, or by protesters at protests. And you can speak into the megaphone, it will amplify your voice, and you can adjust the volume. So you can basically, make your voice very loud or just a little bit louder than it usually is. And so having each of the demons have a megaphone with an adjustable volume allows you to do something like this. Once you have asked the whole system to classify a set of letters, say 50 letters, and you find that it's misclassifying some of them, it has, say, an 80% accuracy rate, then you can carry out a procedure like this. You can randomly adjust the volume slightly and then run the test again and see whether or not the system improved. You can do that after you get an improved system through that random variation. Then you can try random variation again, another set of random variations and tests. And so by doing that repeatedly, you get a result that today is called hill climbing or gradient ascent, which basically means you're inching closer to an optimum system overall by basically adjusting the weights and finding out whether the system with the adjusted weights does a better job